Okay, so we just learned how to use the ICE table to help us calculate or organize information in equilibrium situations so that we can calculate things that we want to calculate, whether that be initial concentrations, the change in the quantity of reactants or products, or the equilibrium concentration of the species. Now we're going to use two methods to simplify some of the more difficult equilibrium problems. These are generally called approximation method, and you'll see them being applied to situations where k is either really small, so we call that the small k approximation, or in situations where k is really large, so we call that the large k approximation. And so we'll start with the small k approximation and just sort of explain what that is. As we know, if k is a small value, much smaller than 1, typically in the case of this approximation, anytime it's less than about 1/100th or 0.01, then we know that very little of that reactant actually goes to form product. So what we can say is that when we look at the change of the reactant with respect to what we start with, the change is very small. So what we can assume happens is given by this expression right here, which is that our equilibrium concentration of reactant, which is usually the starting reactant concentration minus the change, would just be approximately equal to the initial reactant concentration. So again, the assumption is the equilibrium concentration of reactant is approximately the same as the initial reactant concentration. Now, turns out that when we make this assumption, we can simplify some of the math behind equilibrium problems and help us get to the answer much faster. Now, anytime you make an assumption, you have to check whether that assumption is reasonable in terms of the error it gives you, because you're going to have an error when you assume something. In the case of the small k assumption, we say that if the error is 5% or less, then the assumption is good. However, if the error is bigger than 5%, then we can't really use the assumption in this case, so we will have to solve it directly. Which just means that you're going to have to use either the quadratic formula, as we saw in the previous problem, or successive approximation, which is yet another method of math that you learn in your lab. So let's take a look at this problem to illustrate the idea of small k assumption, okay? The reaction is given here, I2 goes to 2I. It tells you that the equilibrium constant is that value. And then if you start with this much of the I2 in 2.3 liter flask, what's the concentration of the gases at equilibrium? Okay, then I set up the ICE table, as you can see here. Now I plug in that number 0.0198 because I've gone ahead and calculated the concentration of the I2, which is just the number of moles divided by the volume. So I get that concentration. I know initially there's no I atom because they didn't give us that information, so we assume that that's 0. That means our change is going to be minus x and plus 2x, so our equilibrium concentration expression should be that. Okay, now when we let that equal to our k expression is I squared over I2 concentration. The I itself is 2x, so 2x squared, and then the I2 is just this 0.0198 minus x, and that should all equal the k value. Now, once you get to this point, there's really two ways to solve this problem. If you don't know anything about small k approximation, you would just directly solve this problem using the quadratic formula. So you're going to just cross multiply that expression, get it to the quadratic equation form, ax squared plus bx plus c, and then use quadratic formula. So I would leave it up to you to find that the x in that case would be 4.29 times 10 to the minus 4 molar. The second method is the approximation method. We start with this expression, which is the product over reactant concentration equals to the k value. Okay, that's exactly where we left off earlier before we went to the quadratic, which is this part right here, right? And so how is the assumption making our life easier? Well, remember, the assumption, what it's saying is that the change is small relative to the initial reactant concentration. So the equilibrium concentration of the reactant would be the same as the initial reactant concentration. Another way of saying that is that x can be ignored. That's the small k assumption. So then you can write it like this once you make that assumption. Bottom part would just be 0.0198 equals to 3.8 times 10 to the minus 5. The calculation becomes a lot easier to do than a quadratic formula, because all you need to do is say x squared equals to 3.8 times 10 to the minus 5 times 0.0198 divided by 4, and then you just us solve for x. What you end up getting is 4.34 times 10 to the minus 4 molar. Now notice that the answer without approximating is 4.29 times 10 to the minus 4. The answer with approximation is 4.34 times 10 to the minus 4. So you can see that the difference between those two numbers is not huge. In fact, you can check your answer. The way you check your approximation is take the difference of those two numbers and then divide it by the correct answer and find that percent error, right? 4.34 times 10 to the minus 4 minus 4.29, which is the correct answer, times 10 to the minus 4 over 4.29 times 10 to the minus 4 times 100%. You end up getting 1.1%. Now, of course, that means that your error level is way below that 5% cutoff that we said we want to use. So that assumption is acceptable. And in fact, it makes our life a lot easier mathematically. Hopefully you can see that. Now, that's not the actual answer, right? Because they're actually asking us for concentration at equilibrium. So you're going to need to plug in that x value into each of those expressions, 0.0198 minus x and 2x, okay? And if you do that, then you're going to get your actual answer to the question. And in this case, use the x value that you get from the approximation method, because that is a reasonable method to use in this situation. You will see that the small k approximation is very, very useful in some of the equilibrium problems that we will encounter in the future, both in acid-base chemistry as well as in solubility equilibria. Okay, so we just discussed this method of simplifying equilibrium calculations called the small k approximation or small k assumption. Now we're going to go to the other side when you have reactions with really large k, which in this case is defined as anything greater than 100. You can use something called a large k assumption. When you have reactions with really large K, it implies that much of the reactants is consumed to make product. That's what we observe with reactions with really large K. So the assumption here is simply that all of the reactants are consumed in the reaction. This is the kind of calculation that we always did in Chem 11. We assumed that one of the reactants, which we call the limiting reactant, is completely consumed. And as a result, we just need to calculate how much of the other reactant is left, which we call the excess reactant, and we can also calculate the amount of product. That's what the large K approximation is. It's basically the same kind of calculation you did in Chem 11. However, there's a slight modification which is given in step 2. We need this step because in reality, the limiting reactant is not completely consumed in a reversible reaction. There's a little bit of it that's left. So we can calculate that by reversing the reaction and then using the small k assumption. So this step 2 is sort of the equilibrium calculation component of it for this standard reaction. So let me show you what I mean by that. It says the equilibrium constant for this reaction, H2Br2 goes to 2HBr, is 2.18 times 10 to the 6. Look at how big that number is. Right? It's a million. And then it says starting with some quantity of H2 and Br2, calculate equilibrium concentrations of all species. Okay, so I'm going to start by writing my reaction, which is H2Br2 goes to 2HBr. I put in the initial values here. I got this by calculating the molarity using the number of moles and the volume that I was given. My product originally is 0, so minus x plus 2x. So this is my equilibrium concentration expression. So now, if I don't know anything about large K approximation, I'm just going to go ahead and do this with quadratic equation. So you just solve it directly. That would end up actually giving you x equals 0.083. Now let me point out, going back to the ICE table, if x is 0.083, okay, notice that that's exactly the same number as the initial reactant concentration for Br. So therefore, if x is the same number, that means that this is really just 0, right? So another way to say that is Br2 is the limiting reactant in this case because everything is used up for Br2. Therefore, you can calculate how much of this is left. That would be your excess reactant. It would just be 0.267 minus 0.083. And then the HBr would just be 2 times 0.083, right? So that will be a direct method. So now we're going to go to the second method, which is our large K assumption. So this is a new part, right? So I'm going to walk you through it. And we start with our initial concentration. And then this is what we're going to do. We're going to assume that one of these guys is a limiting reactant. Now, the reactants both have coefficient of 1. So to figure out the limiting reactant, all we need to do is just figure out which one is the smaller one, because that's the one that's going to go away completely. It's pretty clear that the smaller one is Br2. So I'm going to just say all Br2 is going to go away. Okay, that's not the truth. That's the large K assumption. Once we say that, then of course by stoichiometry, this also has to be 0.083. This side has to be plus 2 times 0.083, which end up being 0.167. What do we get at the end? We got 0.184. Subtract those, we got 0. I'll put a little approximate 0 there just to indicate that it's not really 0. And then this one is 0.167. Okay, so immediately once you do that, you already actually have the answer to two of them. This one and this one. You already found the equilibrium concentration. Now, the one that is not quite right is this one right here. This number is not really 0. And that's where that second step in the large K approximation is introduced. Okay, we're going to reverse our reaction. Why do we reverse it? Because in a reversible reaction, the limiting reactant is not completely consumed. There's some small amount that's left. We can calculate what this small quantity is by reversing the reaction. We write 2HBr goes to H2 and Br2, again using the ice table. So all the numbers that you have here as equilibrium numbers would be your initial value of the new ice table. 0.167, 0.184, and 0. Now, as we know, if we have no product, the reaction has to go to make product. So that means this is minus 2x, plus x, and plus x. So our final equilibrium concentration would look something like this. Now, what is our K now? Well, since we're reversing reaction, that means it should be 1 over, or the reciprocal of the old K, right? The old K being the large K value that we had earlier, which was 2.18 times 10 to the power of 6. If we take the reciprocal of that, we get 4.59 times 10 to the minus 7, which is a small k value, allowing us to use the small k assumption to solve the problem. Well, how do I find x? Use the k expression again, except that now this is for the new reaction. So H2 times Br2 over HBr squared, 0.184 plus x times x over 0.167 minus 2x squared. And that's supposed to equal to the new k value. You're dealing with a really tiny k here. So if you're dealing with a really tiny k, that means you can use the small k assumption. And that means we can ignore the value of x when it's compared to initial concentration. We can say that this number plus x is approximately equal to just 0.184. This number minus 2x is approximately just equal to 0.167. So the equation has simplified now to the following: 0.184 times x, and this was the x that was originally there, which we didn't remove because it's not being compared to an initial concentration. And then we have at the bottom 0.167, and it's still squared. It's the 2x that we take away, not the square. And then we have 4.59 times 10 to the minus 7. When you have that equation, it's really easy to just isolate the x on one side and put everybody else on the other side. And that would leave you with x equal to 6.95 times 10 to the minus 8, which is actually the same as the Br2 concentration at equilibrium. Remember, that's what our ice table tells us. So right here, I'm just showing you the ice table that x is Br2 equilibrium concentration in this reverse reaction. Okay, so then what that's telling you is that there is some quantity of Br2 left at the end, but it's a really tiny number, and that's what we expect. We expect it to be a really tiny number because this is a large K reaction, so most of your reactants become products. So your original reactant, which is Br2, that we say is the limiting reactant, there's a little bit of it left at equilibrium. And that's exactly what this is, just to complete the unit there. And that's how we use the large K assumption method. Since we use the small k assumption method in the second part of the problem, we're going to have to check whether the assumption is reasonable or not. So the check is the following. Remember what we assumed was this, right? We assumed that 0.184 plus x is approximately equal to 0.184. And then the other assumption we made is 0.167 minus 2x is approximately equal to 0.167. So now that we know what our x is equal, we can plug it in and see if the x is really that small. So there are two numbers to check here. So do you need to do both of them? The answer is no. Check the one that is smaller, right? So which number is smaller in compared to x? Well, it's going to be this one right here. It's 0.167 to compare the 2x. So if that satisfy our requirement of 5% error, then we should be able to assume that the other one also satisfy our requirements. To check, we just take the assumption, which is the 2x, divided by the 0.167 and then multiply by 100%. And we just want to see if that actually is less than 5%. Our x value itself is 6.95 times 10 to the minus 8 divided by 0.167 times 100%. And turns out that what we get is something like 8.32 times 10 to the minus 5%. Okay, or another way to write it as decimal form would be something like 0.00008 0.32%. As you can see, that's way smaller than 5%. So our assumption is reasonable.
So let me summarize the two assumption methods that we just discussed. The first one is when your k value is less than 0.01, use the small k assumption method, and at the end, check to make sure that your error is less than 5%. When the k is larger than 100, use the large k assumption method, which has two steps in it. Step 1, you assume that the reaction goes to completion, or another way of saying this is you assume that the limiting reactant in the reaction is completely consumed. Once you do that, you have to reverse the reaction, this is step 2, to give you a small k reaction, and then you will use the small k assumption to solve for the concentration of the limiting reactant.